use graphics libraries and use specific programs. But no one wants to take their scientific code, which is written in Fortran, and write C graphics libraries programs for it to get to run GPUs. So people have developed ways of exploiting these GPUs, which are not as nasty as writing low-level C and using graphics primitives. But they still mean you have to take your code and do something to it to get it to run on the GPU. Now I should say, the background to this is that 98% of the programs which run on big parallel computers are C or Fortran. Okay. So about 50% are C and about 50% are Fortran. So for these things, Xeon Phis or GPUs to be any use, they need to be efficient. You need to be able to really take Fortran programs or C programs and use them on there. We don't really see many C++, see any Java, we don't really see any Python or anything like that. It's C and Fortran programs. And that's primarily because, well, I've got a graph later on. The main codes that are using these systems have been around for a long time. 20, 30, 40, 50 years. Big code bases, million plus lines of code each. And they're either written in C or Fortran. Actually, a lot of them are written in Fortran. So, but C and Fortran by themselves don't support using accelerators, don't support using the graphics cards. So you have to use something that enables this program to use that hardware. Okay. So, and then there are also other considerations when using these things. So primarily, traditionally when we're writing parallel programs, you have over the past 20, 30 years been writing using something called MPI, right, which splits up your programs and sends messages between them. And you can use this to run on very big systems, and people run up to tens and hundreds of thousands of processes of code using it. But the accelerator model is slightly different. So we now have these computers which have nodes, and inside the node it has processor and then accelerators, and then all these nodes are connected together by a network. So to efficiently use this system, unless you just want to use one GPU or one Xeon Phi, and for most of our scientific programs you can't do that because we don't have enough memory inside them to be able to do useful simulations on them. You need to be able to use these things together. So you need to have a way of, your MPI program goes across the nodes, splits up your work. But then you also need to choose how you split your work upon the GPU. And the GPUs have, and the Xeon Phis have quite a lot of things inside them. Hundreds or thousands of cores inside them. And so you have to sort of work out how you're going to take your program and map it onto those hundreds and thousands of things. How you do that, decompose the problem onto hardware. Okay? And then once you've done all that, you can probably get your code to run. But actually, in general, your code probably won't run very well because there are a few things you may have to do to optimize it. So it's generally a process of taking your code and deciding how you're going to decompose the work across the accelerators, porting it using some specific language features or library features, and then optimizing it and get good performance out of it. So one of the main ways that people program GPUs is using what's called CUDA. And this is a language extension written by NVIDIA, who are the people who sell most of the scientific GPUs, allow you to program C++ programs and use GPUs through them. So CUDA has this language and is built around this concept of kernels. And the kernel is the thing that you're going to run on the GPU. So you write your code, you alter your code, and you say this bit is a kernel, and this bit will run on the GPU. So that's how you define the bits of work which you're going to split up across the GPU. And then it also, CUDA gives you then some APIs, some functions, some library calls which say you can copy some data to the GPU, you can copy some data back from the GPU. So you can manage, you have to explicitly tell it which bits of the program to run and how you move the data there and how you do it. And actually that's one of the biggest challenges in optimizing codes for GPUs is that the GPUs have fast memory themselves, but the connection between the main memory and the GPU is quite slow. So if you're always moving data backwards and forwards between the GPU and the main memory, that's going to kill your performance. So that's this memory management is one of the areas where you really have to spend a lot of time optimizing the work. And that's fine for C and C++, but that's no use for Fortran really. You don't really want to have to take parts of your Fortran code, rewrite them in C, and then call them for your Fortran code, which you can do, but it's not very nice. Yeah.
One of the things with memory that doesn't seem to be stressed is you also have a problem getting data into the GPU core.
Right.
And unless you're effectively using the caches, you can get very poor performance. What should be giving you a very high floating point performance, but
So you mean coalescing memory and things like that? You mean coalescing?
Not necessarily coalescing. It's just if you're not effectively using the cache, so that you're always fetching it data, whether it's coalescing or not, you can still get very poor performance.
So I will talk about performance issues a little bit later.
Okay. But
good bound and memory bound.
Yeah, I mean, primarily the GPUs, the NVIDIA ones, are designed to be massively oversubscribed, so you hide your memory data to start with. And if you don't do that, then you know you won't get good performance. But yes, that's all well and good for C and C++, but of course a lot of that programming in Fortran. How can you deal with that? Well, the PGI compilers, which are now owned by NVIDIA, had an extension which let you write CUDA-like code for Fortran. So PGI applied a port of this CUDA stuff for Fortran. NVIDIA GPUs have a concept of a two-level hierarchy in them. We have these streaming multiprocessors, these blocks, and then inside those, they each have multiple cores with some shared memory. So the NVIDIA GPUs have this sort of concept of streaming multiprocessors. You've got a number of those on a GPU, and then inside each one of those, you've got a number of cores. This is a sort of an abstraction of the hardware, which is designed to make it easy to port between different GPUs, because you don't have to care exactly how many cores and how many blocks are there. You should be able to take the same code and run it on different GPUs, which have different numbers of cores, but it still maps this general concept that you have one level to break your program down to, and then another level of this how you write. Okay. So in CUDA, it abstracts into a grid of thread blocks. So the grid maps to the first level, and the thread blocks map to the second level. And you don't need to care about exactly how many cores are inside the CPU, inside the GPU, and how many blocks are inside the GPU. The system is designed for you to oversubscribe, to try and run more things than you have hardware to support, many more things than you have hardware to support, and then it will just look after them all for you. And it does this lets you hide your memory latencies, hide your memory accesses, because whilst one set of threads are waiting for data to be loaded to a cache, another set can be loaded into the second. If you're running enough things at once, then it should be able to give you quite good performance. This is how the system is designed to run. So, this is, quite a small loop. This is the kind of common bit of code we have sitting inside our scientific simulation. We've got some kind of matrix, some kind of vector in this case, and we're doing an operation on it. And this is parallel in nature because there are each iteration of the loop is independent. Okay? So we can do them all at once if we want. So I skipped over this picture because I put it in the wrong order for some reason. Yeah. But this is the idea for GPU computation, scientific GPU computation, in that most scientific applications we have some kind of data structure where we're going through and doing operations to it. Here we've got a two-dimensional matrix where we're going through and do some operations to it. And the idea here is, well, we've got a GPU with lots and lots of cores on it, and each of these operations is independent, but we can do more of them. So we can assign all these operations to different cores and they all happen. So this is how we get our parallel performance. So how do you actually do that in CUDA? This is C code, but we're going to take this loop and we're going to try and turn it into a kernel which will run on the GPU. So then CUDA, C CUDA, gives you a number of language features which let you do that. So the first we can see here is that instead of this just being a loop, we've turned it into a function. Turned it into a function because we need to offload work to the GPU, and CUDA does that by offloading individual functions to the GPU. And you have these specifiers which you can add. So you place a loop of a function, you add the global specifier, okay? And this is to specify to compile this is going to become a GPU kernel. And then we can use some internal CUDA variables which the language provides to you to tell you how you map this work to the different cores in the GPU here. So what we can see here, instead of having a loop from 0 to n, we've just said this is a function, and we're only in the function we're only doing one operation, which is doing C of I equals A of I plus B of I, and we define I here to be a thread ID, okay? And this is something which CUDA gives us. It says, give me a thread ID X in this case, and then when we run this, as long as we run it on the right number of threads, then it will run multiple copies of this, enough copies to do all the operations that we did in the original loop. Okay? So in this particular example, we then, in our code, we have this function we defined, and then we have these special things, and all these brackets are needed. So running using multiple CUDA threads, you have this bracket syntax, and we say, how many blocks per grid am I going to run, and how many threads per block? Okay. So if we remember the picture I had before, where we've got this two-level hierarchy, we've got blocks in a grid, and then threads in a block. Okay. That code that I was just running there, which just as a single loop from 0 to n, what I was going to say is I want to run that, I only want to use one block, because I've only got one dimension of my vector to do, and then I want to assign 0 to n threads to this block. So when we've run it, we've said number of blocks per grid is 1, number of threads per block is n, these are my data structures I've passed in, and that will run that loop for us on a single part of the GPU, and it will do the calculation once we will do the number of iterations we wanted. Of course, this isn't efficiently going to use a GPU because we have multiple blocks in that GPU we're not using one. We're only using one of them. But then there may be a different part of your program which could use the other blocks which are being used at the same time. Actually, most scientific programs, you're not doing a single dimension. You're not doing a loop over a vector. You're doing a loop over multi-dimensional data structure. So in practice, that one was fine, but actually we may want to go for multi-dimensional data structures. So we may want a 2D or 3D data structure. We may want to use multiple blocks and multiple grids. So we can define this. We can define these in different ways. So here we've still got vector, single-dimensional vector, but we're going to say our vector is going to be quite long here. So instead of n being, the size value being quite small, it's very big. So if we had a loop over 1 million elements of vector, and we just stuck them all on one block on the GPU, that would be very efficient. But we can say, well, we can actually try and split up each part of that vector into different blocks on the GPU, and then we go. So we can do that by actually saying, well, the number we're going to choose 256 as to be the number of threads per block, and then choose as many blocks as you can split that up into. How many 256 you have in your full vector. Assign that out.